Okay, so let's give you an example. Um, Self-interstitial mediated self-diffusion in FCC. When you visualize the term we call a self-interstitial mediated, actually, and self-diffusion. Self means the host. So we have the host atom at interstitial site, and it will drive the self-host diffusion in FCC. Then this actually just tell you this is belongs to interstitial C mechanism. And the question here is we have three split dumbbell self-interstitials. Split dumbbell, which means that you have two host atoms share one lattice point. And this we have this type of self-interstitial defect. And with 100 configurations and FCC structures, 100 configurations. So this is a direction. So it can be 100, 010, or 001, right? As we mentioned before. And the question A asks you what are the flux of this self-interstitial, uh, or what's the flux of the host atoms from alpha to beta and beta to alpha, and also what is the net flux in terms of total concentration of interstitials per univalent C, and also total jump frequency. So based on the questions, actually you know that they ask you to get the D host diffusivity, diffusivity of the host atom based on the fixed phase law. So they highlight we need to get the net flux, right? And they also ask you what is the diffusivity of the split dumbbell self-interstitials, as I mentioned. But the diffusivity they are not they not ask about the host diffusivity. They ask about the split dumbbell self-interstitials in terms of C gamma and lattice constant. So the diffusivity is this self-interstitials. Here will be the split dumbbell self-interstitial in terms of C gamma and lattice constant. 所以从这里，他问的问题就是，因为这个题目的话，它如果是像刚刚出的，就是它是一个，他告诉你说它是一个 self-interstitial mediated，然后 self-diffusion，那 FCC，那基本上你就要先画出 FCC 的结构，然后 self-interstitial 讲的是我有一个 host atom 站在 interstitial site 上，那这 interstitial 就有很多种嘛，那它又是 mediated self diffusion 是 host，所以通常 self 在这里都是 host，从这里就可以知道，其实讲的是 interstitial C。那也就是说，在 FCC 里面有 speed dumbbell，这个 self interstitial defect 在这里讲。有6种里面，它专指 split down。它在这一个问题里面，它问的是 这 split dumbbell。那 split dumbbell 的话，就会有3种方向嘛。它有连线，2个原子连线有3种方向，100、010跟001嘛。那他有跟你说，就有3种 configuration。然后他希望你用，因为有 net flux，说他希望你用 fixed phase load 解。那他问你的是 split dumbbell 后来的 diffusivity，还不是问 host，所以不用 xi、dif。OK， so first of all, in order to solve those questions, you can usually I will use to draw like 2 unit cells for FCC, and because it's self-interstitial, because it belongs to split dumbbell, right? So all the atoms occupy the lattice point. So here I draw like also share on the shared face, I draw 3 different types of configurations of this split dumbbell. Can be 100 along x-axis, can be 010 along y-axis, and also can be 001 along z-axis. If the question didn't highlight the ratio of 3 different configurations of split dumbbell, then that imply that they are the percentage are the same, so it should be 1 out of 3 for each one. So due to I need to solve this based on fixed phase law, so first of all I need to determine where is alpha and where is the beta. So here I define here will be the alpha and this will be the beta. So why? Some people always ask me why, because I used to the way I learned the split dumbbell would be uh, focus on the shear plane at the center, face center here. So let's if I use this as an alpha plane, then that would be the more familiar case I have or I have learned in this line. And as long as this is alpha, then the nearest plane can be beta. So nearest plane with the latest point will be at the center. So I will choose here as a beta. So next, so I need to draw some where because I need to know the possible jumping directions, so I need to highlight how many possible jumping side I can this atoms host atom can jump, right? But here all the sides should be at latest point. So will be the face center here, face center for the inner plane, face center at the outer plane, and face center of the bottom plane, because the host atom jump in substitutional side. The case we just learned, right? Interstitial and jump to substitutional, also the latest point. So here will be这边可以跳的要记得跟前面不一样，它是去挤那个在金格点上面或 substitutional side 的，所以在这里的话就会是这四个上面、下面、前面跟后面的面型。So we only have four possible lattice point can allow the host atom or one of the split dumbbell jump. Okay. So next, I try to formulate J alpha to beta as long as I get the JR flux of the host atom. Or let's split dumbbell. Sorry, let's split dumbbell from alpha to beta. Then I can use the same trick to formulate beta to alpha in terms of the concentration part. So let's try to formulate the flux from alpha to beta. So the first one I will focus on the split dumbbell along 100 be the red one. So how many possible jumping directions for both these atoms? Nearest one. So because they along X, right? So the nearest one should be this one. This one will be jump to hit this side, and this one should be jump this side. So two directions. So I have two directions, and the concentration will be 1 out of 3 C prime. Because I have know that they have 1/3 C prime and gamma prime. So this is a possible directions gamma prime, and this is a possible ratios. And for the other, I will consider will be the blue one. Blue is like you link them together, so the direction will be along parallel with y-axis, so it will be 0, 1, 0. So let's pair only this one. Right-handed blue atom can make a successful jump to beta and have 4 directions. This 4 can be jump here, 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 or here. So it's 4 times 4 gamma prime. Then the concentration will be C prime divided by 3. C prime here also the area density. And next will be the last one will be the split dumbbell 001 along z-axis. And the nearest one probably for upper black atom, the nearest will be the upper, and the bottom one nearest will be bottom. So I have 2 gamma prime, and the area concentration will be C prime divided by 3. So I sum 2, 4, 2 together, I got 8 gamma prime. And due to C prime should be converted to valence density, so I also try to draw the valence to contain them. So would be also C times A divided by 2. So I got 4AC gamma prime divided by 3. Okay, so but here the question, I mean the answer asks you in terms of C, I have C. So we so here we need to convert the area density C prime into volume density. So you need to pick up a cubic to containing this plane, alpha plane, and without additional ended extra atoms here. So I will pick up this one, and the width or the length for this the cubic will be A divided by 2. So you have a quarter A here and the other quarter here. So you got a quarter plus a quarter, so it will be A divided by 2 here. And next, we just simply get for a C gamma prime 3. But based on the questions, actually they ask you to express in terms of volume concentration and also the gamma. It's a total jump rate, not a gamma prime, the jump rate alone or in specific direction. So we need to convert it like gamma prime to gamma based on the equation or based on the possible directions you determine in based on the equation. So here actually the possible jumping directions for this pair will be 1, 2, 3, 4, 1, 2, 3, 4. So it will be 8, and the distance here also you got the distance is the distance between this and this, that is point. So it'll be 8 divided by square root of 2. So based on this idea, oh, actually that the R layer, because we in this case they did not ask you to convert it in R, not in R, is already in A, right? So it'll be okay. But just to remind you that the possible jumping directions is not the direction you just determine in here. Actually, this Z will be the one you determine here. Okay. So back to here, because you already have a volume concentration, so we just use the trick we told you before, is we use the C plus dy, partial C partial y, to represent the concentration of the self-interstitial defect on the beta plane. So we got dy partial C partial y. And you use this J alpha beta to minus J beta alpha, then you will get a net flux for this self-interstitial defect. You only this minus this one, so you only have like the second term will be shown here. So we know the diffusivity equals to A squared gamma divided by 12. Okay. 所以在这里的话，就大家记得两个小的 trick，就是你在得到这个平均的，就是面密度变成体密度的时候，你要找到一个面积，然后它是一个体积，它要包含你刚刚讨论的那个平面，但它不能增加这个体积里面不能有增加原子数。然后另外一个就是在当题目问你就是不要你用 gamma prime， 要你用 gamma 的时候，这个 possible jumping direction 这个判定要用这个公式解的判断，而不是用我们刚刚从这个平面跳到这个平面的这个possible 的 jump direction， 好不好？So the question C will be the population of 3100 self-interstitial will change with applied stress. When the stress is released, the concentration of 3 self-interstitial will repopulate and reach the state 1 over out of 3 times C total. Show the relaxation time for this repopulation is tau equals to 2 divided by 3 times gamma. Okay, so you can have a look on the lecture 2 on page on page 68 in PPT slide. tell you about when you have the tension stress, when you apply a tension stress along 100, 100. So uh, which means that the other directions will feel like compressive region. So the atoms, the interstitials at compressive region will move to somewhere feel or in tension region. So which means that the concentration of the split dumbbell along 100 will increase. This increase actually contribute from the split dumbbell along 010 and also 001. So the beginning or initial boundary condition would be I have the higher 100 split dumbbell in the beginning, but this concentration will be higher than 1/3. But when I remove this force, then the split dumbbell along 100, the atom will be jump back, right? So diffusion will happen. And finally, they will reach 1/3, finally. So what is the relaxation time? Please show me that the repopulation time is equals to 2/3 times gamma. So first of all, we need to think about what happened what really happens here. The speed dumbbell 100 will jump to 010 or jump to 001. And some of the speed dumbbell will jump back to 100. So we have the speed dumbbell 100 probably will jump here or move to 010 or so I have less equations and reaction. The rate constant forward I call a K1, but if a reverse reaction, I call a K3 rate constant. And also they can probably one of the atom will move out then to form the speed dumbbell 001. So I have forward rate constant K2 and reverse K4. So in order to like persuade you or make things that more uh can you I hope that you can have a picture what means speed dumbbell move from 011 move to 010. I have in the beginning I have lots of speed dumbbell along 100. It's like this pair, right? This is x-axis, so it's along 100. As long as this uh green atom jump to the jump to here. Actually, here is the center of the front plane. Then you will form the split dumbbell 010. Or it jump to right-handed, also the center of the front plane. 所以它就是绿色的，只要往前跳跳到前面的这个面型去挤这个的话，那现在你就可以看到 speed dumbbell 从原来的100，然后变成现在连线横的就是010。So and this is possibility, right? And you have two possible jumping direction for green atoms, but the back one you also have red atom, right? Every atom probably can jump to back side, the center for the back plane also have become 010, and the second possibility will be like here. So you have 2 plus 2, so 4 possible jumping directions. So I have 4 gamma prime for 100 for K1 and also K3. If you try to reverse it, also for gamma prime. And I also show you the other possibilities. 100 move to 001. So the same idea was 100. And 001 actually is along the axis. So the green one probably jump to here, and the red one back to lattice point. So you can see split dumbbell moves from 100 to 001. This is one direction, two the directions, and the other possibility is the red one to jump to upper and bottom, also for gamma prong. So K2 is for gamma prong, but if you try you can also try to draw this 001 back to 100, also for gamma prong. So this is how we get the rate constant. And next, I want to formulate because they asked me about the relaxation time. Relaxation time means the concentration drop decrease to 1 to -1，就是一的负一次方的浓度降成原来浓度的一的负一次方的时候，时间是多少？ Okay, so I need to, because it's talking about the concentration change rate, right? So I need to formulate this concentration change rate of the 100 split dumbbell can be write down K1, this concentration, K2, this concentration. This both will decrease the concentration along 100. But 010, if back the reverse, K3 will increase, right? So I have a negative K3 concentration 010, and K4 also increase. So I have a negative K4 concentration 001. As long as I can solve this equation, I know how the concentration change with time. And this moment will be the relaxation time. So I also know K1, K2, K3, K4 belongs equals to 4 gamma prime. So this will be 8. This will be I times the negative term together and also put the 4 gamma prime to substitute K1, K2, K3, K4. So I got the negative 8 gamma prime plus 4 gamma prime plus 4 gamma prime here. And I also know the very important trick here. I have a -8 gamma prime, and on your right hand side, I got the 4 gamma prime to 2 directions. And I also know the good but important information here, the total concentration for all split dumbbell. I know the concentration equals to constant, which is the total concentration for split dumbbell equals constant. But here I have two of them, 010, 001. If I can get 100, then I can simplify this equation. So I use trick to modify this term to as a -12 plus 4. So also -8, right? But this part I can combine them as a constant here. So I rewritten this, I rewritten this equation, copy here and -12 gamma C100, and here would be plus 4C total. So I rewritten, I have simplified the equation, show like this. Next, I'm going to solve this equation. So I use this familiar mathematic engineer mathematic trick. This is y. Y equals to concentration, and B equals to this C total divided by 3, and A equals to 12 gamma prime. So this equation, I know the solution here, so I just copy them. So Y here, so I got the Y. This is Y is C concentration along 100, Y minus B here, B equals to K. This is K exponential, and A is -12. Oh, sorry, it's 12 gamma prime, 12 gamma prime times T. So I don't know the K, right? So I need the boundary conditions. As long as T equals to 0, then Y minus B will be at T equals to 0, will be this result equals to K. So I know the K here. And you also can double check whether when the T approaches to infinity, so you also get the C total. Okay. So here, so as I mentioned, the concentration dropped to E to -1. So you know the gamma prime. The tau here would be 1 divided by 12 gamma prime. And gamma prime equals 8 gamma prime equals to gamma. So now I successfully prove the realization time equals to 2 divided by 3. Okay. So do you have any questions? So based on here, if you don't have any questions, then this is like we don't have any real parameters to I did not give you any real parameters here, right? So I transfer these questions into more real questions. So consider we have a split dumbbell self-interstitial defects in copper. And I also assume the atomic jump frequency gamma prime equals to 10 to 8 per second. Lattice constant show like this, and the concentration for split dumbbell show like this, and concentration the number of split dumbbell like this, and also the numbers of copper or concentration of coppers is shown like this. So could you calculate the differentiability of split dumbbell defect? So it's a split dumbbell, so it should be like this. So if you put all the parameters inside, you should get this value. I hope you can practice this. And also, please calculate the self-diffusivity of the copper. Is copper not split dumbbell? So it should be XIDIF. XIDIF. So XI, use this. Combine this, you can get XI, and DI, you have the ref here, and F, so you can get these results. And when the copper is subject to a compressive stress along 100, now it's compressive stress. So compressive, so it's compressive, is reverse force, which means that you will finally get a lower concentration of split dumbbell. Under the situations, we find that the concentration of split dumbbell becomes to 10 to 12. Calculate the split dumbbell after releasing the stress for zero 0.5 nanoseconds. So I give you the time, ask you about the concentration. So I tell you the time, and also ask you about the concentration. Okay, so you can use this one, but slightly different when you formulate. This is compressive stress. So for here, when you formulate this one, so it should be a little bit different. I hope you can have a practice for this one, and also show after series deviation, also show this same results for this case. For this, it can little bit of homework, or you can have this practice. So we already finished the fourth diffusion mechanism we call the interstitial mechanism. So now I'm going to give you a quick summary for this part. Regarding to the atomic diffusion mechanism, we did introduce you besides the ring mechanism, 2, 3, 4, actually, we show you how to quantitatively calculate or estimate the diffusivity, right? And for vacancy one, the host atom actually, because there's a nearby have a vacancy, so the host atom diffuse through the vacancy. So the diffusivity for the host atom is XV/dVF. And this is a diffusivity for the host atom, right? XV/dVF is proportion with this XV is a vacancy formation energy, and also involve like the vacancy migration enthalpy. Sorry, both are enthalpy term. So interstitial mechanism actually is similar with a vacancy one because they're nearby self-interstitial defects. This drive the host atom diffuse. So the diffusivity of the host atom is XIDIF. Based on the idea you learn, will be proportional temperature dependent, will be uh, the self-interstitial defect formation enthalpy, and also less defect migration enthalpy. So this is easy to remember. And the last one, which is both lists talking about the host atom, right? And the interstitial mechanism actually the diffusing atom is solute atom, small solute atom, and always diffuse through interstitial site. And there are two typical types of interstitial site. One is octahedral, and the other one is tetrahedral. Usually, the question should focus or emphasize one type of interstitial site. Okay, so based on here, the energy turn only related with migration enthalpy. So based on this idea, we know that compared with exponential term, usually dominate the value for diffusivity. So this D should be higher than others. And compared to this one and this one, which one should have a higher diffusivity? Would be vacancy one, right? Because regarding to formation energy, this will be smaller. Migration energy, this should be smaller as well. So this one should higher than this one. If we're talking about the same material. Okay. So we almost done with four typical diffusion mechanism, but still one more for supplementary or for reference would be how about the vacancy mediated solute diffusion? It's also vacancy, but the difference would be we have a solute atom. Solute actually you dope something, right? But in this case, you dope. It's not um, the dopant is not as the interstitial site or diffuse through interstitial site. It's some kind of substitutional dopant, which means that your dopant at substitutional site at the latest point. So under this situation, what's a solute diffusivity? So let's a solute diffusivity. So we will focus on here. So just a quick reminder to compare the vacancy and the vacancy mediated solute diffusion. And the structure we talk about actually um, is FCC structure. So how the host atom diffuse? Here, the host atom, we have just one type or one kind of host atom here. And as long as there's vacancy nearby, the host atom will diffuse or exchange site with vacancy. This is what we call the vacancy mediated one. But under this situation, based on the equation solutions, you got the possible jumping directions, jump distance, each jump distance, and gamma prime. And gamma prime actually is involved with the bond strength, reduced mass, and also migration energy. So because we only have one type of atoms, so the reduced mass and beta would be more simple. So only one type of gamma prime is a host atom jump in vacancy. Okay, you only have one type of atom, everything is more simple. Reduced mass, only one type of atom, bond strength, depending on how many bond or what type of bond I have here. But what's the vacancy mediated solute, which means that I have a dopant, I have a substitutional dopant, which means that, for example, I have a solute atom. I dope the solute atom to replace the host atom. Then I ask you about the solute diffusivity for the solute atom. And also uh, the diffusivity also through vacancy mediated one. So this type of diffusion, we call it as a vacancy mediated solute diffusion. So what's the difference between this and this? If you take a look, we also use the same equation here. What would be the difference? Jumping direction should be the same. Each jump distance similar. Slightly just should be the same. Slightly different, probably due to dope the other substitutional dopant. The lattice content probably will slightly change, but not that much. But the big difference will be the gamma prime. Because you have the other type of atoms, so reduced mass and bond strength will be different. So how many gamma prime you have? How many different gamma prime you will have? That will be depending on the because the bond configuration will be different, right? So we do have what you will have solute atom jump into vacancy is one type of situation, right? And the second one will be the uh, host atom, but near surrounded the solute atom. This green one jump into vacancy. So we have the gamma prime, and we should use V similar C as to represent the uh, host atom surrounding solute. So host atom surrounding solute jump into vacancy. And the last one would be the host atom jump into vacancy, the one with similar with this one. So now we have three different gamma prime. Due to configuration will be different. Because some people probably will say, Professor, this host atom are the same type of host atom with this one. Why we need to highlight it? But because they nearby solute, so the bond strength and reduced mass will be slightly different with the less host atom. So I highlight them. So based on beta and slightly different, especially due to they surrounding solute. So we do have this probably this jump, and this jump will be different. So we have three different gamma prime in the vacancy mediated solute diffusion process. So that makes things complicated, right? If you want to know the facility for this solute. So you need to compare what are the difference for the three different gamma prime. So now let's back to here. How solute atom diffuse? So based on we know that there are three jump rate or jump frequency need to be considered. The first one we use as double arrows here, V solute vacancy jump rate. And the green one would be the one I just mentioned would be the vacancy, the host atom surrounding solute jump into vacancy. We use this symbol to represent its gamma prime. And the last one would be the host atom jump into the vacancy, the same with this one, the white one. So now we have the three different gamma prime. Which one will be dominant? The jumping process dominate the solute diffusivity will be the key question. So we need to make a very important assumption here. We consider there's a attractive interaction between the solute and vacancy. Attractive interaction means that we have a negative binding energy between the solute and vacancy. They like to get together, stay together, or like jump back and forth. They like to stick together, so have a negative binding energy. So which means that because they have negative binding energy, this will be have smaller energy, solute and vacancy. So which means that you have a higher exponential term. You have smaller here, value here, you got a higher exponential term. So compared with the so the gamma prime will be higher as we solute vacancy jump rate will be higher because you have a smaller here, so the gamma prime SV will be higher. But compared to host vacancy, so this will be higher. The energy barrier for host vacancy will be higher, so that will lead the gamma prime lower. So you know this one have a lower jump array between the host and vacancy, and this one have a higher, and we still have one more is um, host agents surrounding salute, right? So you can assume this is the lowest one. So we have two more. So there's two possibility for case one and case two. But lowest gamma prime will be the host agent jump into vacancy. And for the case one will be salute jump into exchange with vacancy will be a highest one. Then second would be the host agent surrounding salute jumping in vacancy. And the lowest one would be the host agent jumping in vacancy. And the second case actually just exchange the order between here. The jump array for host agent surrounding salute jump in vacancy have a highest jump array. Then the second one will be the salute jump in vacancy, and the slowest one the same with case one is host agent jump in vacancy. So we have two, under this important assumption, we have two cases. For each case, we need to get what's the DS, salute, the facility for this salute agent. OK。这边有人问我说，就是他不太能 understand why we have three different gamma prime, especially the second one，为什么第二个不一样？那这跟 bound strain 到底有什么关联？大家可以这样想，就是呃也许我用这张图来表达会比较好。那我们可以看一下说，就是你如果要有 如果是 vacancy mediated one 的话，那你 host atom 不是要跳到 vacancy 嘛？那它就要挣脱它的 bound configuration，就是它附近有多少的 bound，它必须要 overcome 这个，它才能 make a successful jump to vacancy。所以这个 beta 指的就会是它拥有的 surrounding 的，它跟附近的伙伴原子有的 interaction 的 bound configuration。所以用这个角度来看，就是舍路这边换成另外一种 atom 舍路的时候，就蛮明确的。它有几个伽马呢？如果它第一件事情就是，如果舍路要 make a successful jump to vacancy，它就要 break out 这一些。但因为它舍路本身它的 mass reduce mass，它的 mass 就会 different with the host one。所以这里就一定会不一样。那它跟它又是不同的原子，所以它的 beta 也会不太一样。所以这就会是一种 gamma prime。然后我们叫做刚刚讲的 salute 跟 vacancy 的 gamma prime。那第二种的话就是这个 surround，就是它是这个一样是 host atom。看一下，它是 host atom，但它是 nearby 舍路的 host atom jump in vacancy。为什么？因为你看它是 host atom，对不对？但是它是当你在看它 bound 的 configuration 的时候，它有一边是舍路 atom，其他都是 host atom，所以它又跟这个 host atom，它附近全部都是 host atom 跳进来，它的 bound 的 configuration beta 会是不一样的。所以我们就有了就会有一个，然后这个就会是第二种，因为像这个跟这个事实上是一样，就是它如果要 make a successful jump to vacancy 的话，它的 bound configuration will be all the interaction surrounded it, right？ 就是它附近的这个，那它怎样呢？它附近就有1、2、3、4个 host，但有一个 salute，所以它 bound 的 configuration 的这一堆就会跟这一个不一样，因为这个的话，它附近全部都是 host atom，就会不一样，所以我们就有3种不一样的。然后希望这样就是有让同学们比较清楚。